Well, welcome to this fairly short video going through how to read the results from a laser diffraction system. In this case, this is a Malvern Mastersizer. I have to confess that the results are somewhat old because this, as you see just here, is the date at which the test was taken, which is back in 2002, so we are going back a little way. But nevertheless, modern devices have a pretty similar sort of layout. It's a little bit more attractive. This is rather basic, but the important things are illustrated here and are relevant to modern presentations. I really want to focus on the statistics, but I'll just say a couple of things about this, the setup itself, which here is called the system details. There's two things here. One is the presentation, which is 4 digits, which are pretty meaningless to anything other than the Malvern database. This is necessary to obtain the correct values of particle size when you're down at the relatively small sizes. Fraunhofer diffraction doesn't actually need the refractive index quite as badly as the basic Me light scattering. If you're going down to small sizes, then you really do need to enter the refractive index for the materials, for the solvent that the materials are suspended in, and that's all tucked away in a presentation file, which is referenced here. Second thing to note is that it's possible to define a monodisperse mathematical model to fit the data to, which monodisperse means that you're just going to get a single peak in the differential distribution, not the cumulative distribution, the one that goes up and comes down, the bell-shaped distribution. This, however, is, as it should be, it says polydisperse, so it could pick up several peaks if they exist. So polydispersed is generally a better distribution to use unless you have good indication that it will be monodisperse. But the thing I want to concentrate on really is this section here, the results statistics. So how to interpret the results statistics for the material. First off, we're in a volume distribution. Volume and mass distributions are the same, so this is really looking at the contribution to the total volume or contribution to the total mass of the distribution of solids in these particular size ranges. So if we just focus on the smallest size, it is between 0.06 microns, or sorry, 0.05 microns and 0.06 microns. So they're the two ranges, the grade boundaries, if you like, and this is the amount of material inside that range, which is obviously 0. And then we have the cumulative undersize just here. It clearly goes off down the bottom, and you might just notice some values here. So we're cumulative value 42.67, less than 22.49 microns. So that's the cumulative curve, whereas the differential is this stuff here in this column. Okay, that's the material between 18.31 and 22.49. But what about the averages? These are really what I want to talk about. Okay, well, the concentration is the amount of material used in order to get the right light scattering, so that's what the concentration is all about. It has to be within a certain range. The instrument tells you whether that's successful or not. The density is something that you input, so it rather depends upon the material. Normally people just in laboratories just ignore that. There's no necessity to enter the density. Putting a value of 1 in just makes the calculation simpler. It does mean that your specific surface area, which is what this is, specific surface area just here, will be incorrect, because you see this is in meters squared per unit of mass, grams in this case, and that depends on having the correct density. So don't pay any attention to that unless you have actually put the correct density in for the solids. So let's talk about it says here mean diameters. That's not strictly true, because this diameter here isn't the mean diameter. That V there represents a volume distribution. Okay, it's already told you it's a volume distribution, but that's what the V is there. It's just restating it. The 0.1 is the 10% value. So in other words, 3.25 microns, 10% of the volume of the distribution, or mass of the distribution, is less than 3.25 microns. 50%, or the 0.5 value just there, is less than 29.76 microns. Okay, well that is a mean, because that is that is an average value, because that is the median value. So the median value of these particles is 29.76 microns. That's the dV 0.5. And then the dV 0.9, which is just over 107 microns, that is the 90 percentile value. So 90% of the distribution is less than 107 microns. Okay, so the 90% value just here, the 10% value just here aren't actually average diameters. However, the median value here, the dV 0.5, is an average diameter. It's the median diameter. Okay, well the mean diameter is a calculated value, and that you can see is just here, 44.11 microns. And how is it represented? It's represented as the D43. You calculate the mean value, and in fact you end up effectively calculating, when you do the calculation you can see where the 43 comes from. But that is the mean value of the distribution. It's always going to be weighted towards the bigger particles, because you're looking for the mean value of the particle by weight. So it is weighted to the bigger particles. I like this value here. This value is a really important one. This is what we call the SOTA mean diameter. It's the surface area to unit volume diameter, and that is called D32. Okay, dimensionally, because we've got a 3/2 here effectively, dimensionally it's got to have the units of a linear dimension, just as the mean diameter, D43, D32. So it has the units of a linear dimension, microns in this case, but the calculation of this is a little bit more complicated. There's certainly a lot of tutorial questions, problems illustrating how to calculate the SOTA mean diameter, but this is down at 8.52 microns. So there are actually 3 average diameters illustrated in this section. The median diameter, which we get directly from looking at the cumulative figure, because the cumulative figure would look something like this. This is amount versus particle size, so you could have that going up to 100%, say, at the top here, 100%, from 0, and from some particle size x minimum to some particle size x maximum, and the 50% value is the median diameter, which for this material is is just under 30 microns. Okay, so that would be just about under 30 microns. So that's the D50, but people call that the D50 typically. Then the mean value by mass or by volume was 44.1. Okay, so here is our mean value by mass down here at 44 microns. 44 microns. As I said, weighted towards the bigger particles, because big particles have more mass in them than small particles. And then the SOTA mean diameter, the surface area per unit volume diameter, that actually is well down below the D50 value at more or less 8.5 microns. And these are all 3 of them are perfectly adequate, perfectly valid averages that we could use to characterize our particle size distribution. The one that is actually probably of least use is the easiest one to use, which is the D50. Sadly, it is greatly overused. The one that normally we should use, especially if we're doing calculations regarding fluid flow, is the D32, the SOTA mean diameter, and you can see there's a massive difference there. 8.5 microns for the SOTA mean diameter, very, very small really, pretty much the same size as your red blood cells, whereas 30 microns was the D50. That's getting to be a reasonable size, and the mean size is even greater. So these are all perfectly valid averages. It's just a case of you have to use the right value in the calculations that you wish to do, and more often than not it's this value down here, the SOTA mean diameter. So they're the averages that the Malvern and other laser diffraction systems provide in a similar sort of way. Okay, bye.